Suppose f of t is a quantity depending on time t. Consider the area which accumulates under the graph of f as time passes. Let us label it cap f of t, for it too depends on time. Now clearly there is some relation between cap f and f. For instance, when f rises more sharply, cap f appears to increase faster, as we see here. In fact, there is an important connection between the two, known as the Fundamental Theorem of Calculus, and we are going to illustrate it in this film. But first, let us briefly review the idea of the rate of change or derivative of a function f with respect to its variable x. Pick a value x0 and an increment delta x, and draw the chord joining the points on the graph of f where x equals x0 and x equals x0 plus delta x. Its slope is the altitude f of x0 plus delta x minus f of x0 of the triangle divided by its base delta x. As delta x approaches 0, this chord rotates into its limiting position, the tangent line, and its slope has become f prime at x0, the derivative of f at the point x0. Thus, the yellow triangle, with base 1 and hypotenuse along the tangent line, has altitude equal to f prime at x0. Turning now to our subject, the relation between a function and the area under its graph, we start with the simplest illustration. Instead of the complicated function we just saw, we take f of x identically equal to 1. In a moment, we will generate f again, keeping track on another set of axes of the area cap f of x accumulating under its graph. Here we see the new axes on which we shall plot cap f. First, let us plot cap f at intervals of 1 unit. Counting the squares, we see that cap f of 1 equals 1, cap f of 2 equals 2, and so on. So the graph of cap f goes through the points 1, 1, 2, 2, 3, 3, and so on. Now let us move in and study the picture more closely. We will plot cap f at intervals of 1/4. This time we must count rectangles, each of area 1/4.
That.
We get the points 1/4, 1/4, 1/2, 1/2, 3/4, 3/4, and so on. Evidently, the graph of cap f is the straight line y equals x, and therefore its slope at every point is 1. Since f of x equals 1 for every x, we see that the derivative of cap f is f. Let us try another case. This time we take f of x equal to x. As before, we will generate the graph of f again and keep track on the other axes of the accumulating area cap f of x, which we shall plot at intervals of 1 unit. This area is always a right triangle. When x equals 1, its base is 1, so cap f of 1 is 1/2. Cap f of 2 is 1/2 of 2 times 2, which is 2. Cap f of 3 is 1/2 3 times 3, or 4.5, and so on. In short, for any x, cap f of x is 1/2 x times x, or x squared over 2. So its graph is the parabola y equals x squared over 2. Let us now measure the slope of the graph of cap f, which is to say, let us find the derivative of cap f by means of our triangle with base 1 and hypotenuse tangent to the curve. If we do this at an arbitrary point x0, we see that the altitude of the triangle, which is cap f prime at x0, agrees exactly with f of x0, the value of f at that point. Thus here again, as in the first example, the derivative of the accumulating area under the graph of f is f. Passing now from these examples to the general proposition behind them, we take a continuous function f, such as we see here. We pick a fixed point a and a variable point x, and consider the area cap f of x under the graph of f between a and x. Let us estimate cap f prime of x. If we increase x by delta x, we adjoin the region we see here, which is roughly approximated by a rectangle with base delta x and altitude f of x. Its area, f of x times delta x, is then a rough approximation to the change delta cap f in the area. In this approximation, we are simply ignoring the small region at the top. Dividing through by delta x, we have delta cap f over delta x, which is just the average change of the area per unit change of x, approximately equal to f of x. As delta x approaches 0, we expect that the approximation will get better, so that in the limit we should have cap f prime of x equal to f of x. Estimating more carefully, we can show that this does indeed happen. As before, we change x by delta x, and look first at the rectangle with base delta x and altitude f of x. Its area, f of x times delta x, is less than or equal to the change delta cap f of x in the area. Now we look at the rectangle with altitude f of x plus delta x. Its area, f of x plus delta x times delta x, is greater than or equal to delta cap f of x. Next we divide through by delta x, and find that delta cap f of x over delta x is between f of x and f of x plus delta x. As delta x approaches 0, the left side, f of x, does not change. The right side, f of x plus delta x, becomes f of x. And delta cap f of x over delta x approaches, of course, cap f prime of x. Hence, in the limit, we have cap f prime of x trapped between f of x and f of x. But this can only be so if cap f prime of x equals f of x. So we may erase the less than signs and arrive at our result. The derivative of the accumulating area under the graph of f is f. We shall achieve a proper understanding of this proposition if we recall that the area under the graph of a function f between 2 points a and b is the limit of the sums of the areas of approximating rectangles, such as we see here. This limit, the definite integral from a to b of f of u du, is indeed the very definition of the area in question. Similarly, cap f of x, the area from a to a variable point x, is, for each fixed x, the limit of the sums of the areas of approximating rectangles. This is the integral from a to x of f of u du, and is called an indefinite integral because its upper limit is variable. Now our proposition is this. The derivative of an indefinite integral of f is f. In this way, the two operations of calculus, namely differentiation and integration, are seen to be closely related. This relation is so basic that our proposition is called the fundamental theorem of calculus.